Hi, in this video, we're going to take a look at model selection in supervised learning. Okay, so at this point in my project, I've met with my stakeholders, I've gotten my data out of the database, I've done my data prep, and I've done some exploratory analysis. I understand my data, I've done my feature selection, I've removed collinear predictor variables, I've removed uninformative predictor variables, I've got down to a good solid list of predictor variables to use. I've done some exploratory analysis, and now I feel confident that I can start looking towards what is the actual model I'm going to use for my project. Now, your project, you might have a limited constraint on what models you can and cannot use. For example, you might be restricted to using logistic regression because that's what your stakeholders are familiar with, or maybe you might have a legal constraint for like a humans resource model. Here, I'm making the assumption that I can do anything I want that I can fit a model for. As long as it's a functioning model to make the best predictions possible, then it's fair game. All right, so how I personally do my model building is that I'll leave my models on default settings, and I'll run through a whole bunch of different model structures, and then whichever ones whichever ones give me the best performance, I'm going to take it a step further, then do parameter tuning and select my final model. Why is it that I do this way? In my opinion, parameter tuning is the least important step out of the entire process. Challenge me and test me on this claim. Compare a model on default settings to your tuned version of that same model, and usually they'll be pretty close to each other. Of course, the tuned version will be better, but not a lot better in my experience. What's more important is the different model structures that we use. So, logistic regression, histogram-based stochastic gradient boosting, k-nearest neighbors, decision tree, etc. That's more important than parameter tuning. So I want to get this step right. Now, I'm still going to do parameter tuning no matter what. It's just that I don't want to spend a lot of time on model structures that I'm not going to use. Like a regular old decision tree, honestly, it's probably not going to make the cut. So I'm not going to spend time doing parameter tuning on it. What I want to do on this step is identify which of these models structures are going to be promising, get down to a short list, and then start doing the parameter tuning process to get the best model I can overall. Okay, so let's go ahead and get into the code. And so, I'm going to run through this. I'm going to load my data. Once again, I'm going to be using the heart disease data set from UC Irvine's data repository. And so here is the original data. One thing that I always do at work is I organize my columns. And so like at work, I'll have a list of ID variables. I call it list ID. And that list will have the names of all the columns that are strictly ID variables. I'll have a list date for all the columns that are strictly dates. If I have control variables, I'll have list control. Here you can see that I've got list predictors, list categorical, list numeric. All right, so list categorical and list numeric correspond to how I'm going to do my data prep on them. So the categorical, either I'm going to bend them until they're binary, 2 levels, and then convert them over to binary, or I'm going to do bending as appropriate, and then I'm going to convert over to dummy variables. Now, the difference between the binary and the dummy variables will have a binary column for every single level. Well, if I only have 2 levels of a categorical predictor variable, I don't need like the repeat. 1 minus a column is equal to the other one. That's redundancy. They're perfectly correlated. I don't need the extra one. So in a moment, I'll show you how I handle that. And now here for the numerics, what I'm going to do in this video is I'm going to apply the Yo-Johnson power transformation. Then I'm going to center and scale to have mean 0, standard deviation 1. And that's a good idea for logistic regression, for support vector machines, k-nearest neighbors. Quite a few model structures perform better if I standardize my data in that manner. Now, if I do that standardization or that Yo-Johnson transformation, and I want to do the interpretation off of coefficients, using a generalized linear model, logistic regression, I've lost that one-to-one correspondence. I can't, because those coefficients are working off the transformed version, not the original. Positive still means positive, negative still means negative in terms of the slope, but it's not an apples to apples comparison. It's like apples to oranges. They're both fruit, but it's not a direct connection. Now, the data set does have missing values in it, so I'm going to go ahead and do median imputation, which I computed previously. And so, okay, here I'm actually converting my target variable to binary. That's not actually imputation, but these two have missing values. And so for CA and thal, I'm going to just put in median of 0 or 3. Now, I could have gone through, done something like misranger imputation, used a model for this. One thing that I found when my stakeholders don't have a really strong of a data background, it's better to give them hard, firm values than it is to say, oh, we built a model to fill in the blanks. If you have a model that is like producing like serious dollar value in decision, it's going to be vetted very, very, very harshly. And if I have a model doing imputation, that model also has to get vetted, and that can add a lot of complications. And so frequently I use univariate imputation, even though it's not as sexy as the other techniques. All right, so now here, I'm going to convert the categorical variables that I would bin into 2 levels, and I'm going to convert them into zeros and ones, and just one column each instead of doing the dummy variable expansion. And so here, if we see greater than zeros, if the resting ECG is greater than 0, I'm going to make it into a 1, and it's 0 if it's 0. If the slope is greater than 1, then it's going to be a 1. If it's equal to 1, it's going to be a 0. And so in thal, if it's greater than 3, it's going to be a 1. If it's 3 or less, it's a 0 off of this. And I find this, this is converting to true false. And then the +1 converts it to numeric. Nice, quick, easy trick. All right, now the other columns, I need to go through and do my dummy variable conversion. And you'll notice that only CP is left. I decided to leave CP as is. And so it's got 3 levels, 2, 3, and 4. And here's my dummy variable conversion right here. Now you'll notice that in my list predictors, I have all of these. All the column names stayed the same on these, but CP got a suffix added onto it when we did the dummy variable conversion. And so in my list predictors, I have it as I want to put it into the actual model. And so here we can see these are our predictor variables. All right, so far I just like to go through, take a look so I understand what's going on a little bit better. You'll notice that the mean is not constant yet, and I definitely don't have a constant variance on my numeric predictors. So let's here I'm going to partition the data. Probably could move this to a different order. And now here is the transformation that I'm going to apply to the numeric predictor variables. I'm going to apply the power transformer function. By default uses the Yo-Johnson transformation. I probably could have used Boxcox, but the power transformer with Yo-Johnson handles a wider range of values, and Yo-Johnson and Boxcox are very close when the data is 100% positive. So I really don't see a loss in using this. The theory isn't as well built up around this one as Boxcox though. Now I'm going to center and scale my data so that I have, with the training data, mean 0, standard deviation 1. The standardization will help many model structures perform better, specifically support vector machines and k-nearest neighbor. All right, and so let's take a look at my training data, just so I have an idea of what I've got. You'll notice that I've got negative values now. So like age is negative, right? So this is the transformed version, not the original version. I can't use this version of the data to talk with my stakeholders because they're not going to really, it's not going to make sense to them. It doesn't even make sense to me, honestly. You'll notice that the Yo-Johnson did a pretty good job of making age cholesterol and thal, no, not thal, I can't remember what it's called. The latch made all of these look pretty close to normally distributed. It did the best it could. It's not quite normal. It didn't do as well over here, but really, I feel satisfied. It would be hard to do better. All right, and now I'm going to double check my correlation. Something I want to point out about this is with my dummy variables. Here are the 3 dummy variables in this corner. They're going to be negative correlated with each other. It has to be that way. The reason for that is that if one variable is a 1, the other dummy variable has to be a 0. If a 0 switches to a 1, the other levels have to switch to 0. It has to be negative correlated, and so we can just see that coming up here. And so one thing I want to do is if I go through, I could potentially reorder these by variable clustering, and it might be easier to spot where do I have collinear predictive variables. This size of the data set is enough that I'm not worried about it with this particular collection of data. All right, so now what I'm going to do is I'm going to go through and I'm going to fit every single potential model structure that I could use for my project. Sometimes you can only use logistic regression. Maybe you can only use a tree model. It depends on what your stakeholders are comfortable with. I would recommend 100% of the time, if you're doing a classification model, that you fit a logistic regression model and a decision tree in addition to all others. Even if you don't use these help guide you on what's going on. You can have a better understanding of what's happening. One single decision tree, the best decision tree you can form, will help you understand your data a little bit better. The coefficients from a logistic regression model can be used to help you understand what's up. And now all of these I have here are model structures that have predict proba in scikit-learn. Not all model structures for classification in scikit-learn have predict proba. Some of them just have predict. If I use the predict method, what it's going to do, it's going to give me like a 0 or a 1. It's not going to give me any form of like probability gradient aspect. I want that gradient because I might want to have to alter what are the cutoffs, you throw in levers, dialing knobs to be able to adjust the output of my final model. And so these all have the predict proba method. Now, something I could do on this, if I wanted to change up something, it would be very easy for me to walk up and let's say that I want to try lasso. I could walk up and I could put that in there. This one, the default in logistic regression scikit-learn is L2 ridge penalty. And so that means that it shrinks down coefficients to help prevent overfitting. And I can go in and change parameters all I want with each of these. And I can put in more of these if there's ones that are important to me. So if I want to, I could do elastic net, I could do maximum likelihood estimation, lasso, and ridge all here very easily. Now I didn't do that because I wanted to keep everything as vanilla as possible for this video to make it a little bit easier to understand. But I could go through very reasonably and adjust different parameters inside here and just repeat the function to be able on this step to try and choose a model structure that I want. That'd be very useful for changing the kernel of discriminant analysis. All right, now on this step, I'm going to go in, I'm actually going to fit the models. And you'll notice that what I'm doing is I'm doing a for loop over this entire list. On each one of these models in this list, I'm going to walk up and I'm going to fit using my training data, which is right here. Okay, and so now I have all of my models all nicely collected together in one list. And so it makes it easy for me to iterate over them and perform computations. So by having everything in a list here of my original models and everything in a list here, after I fit them, this sets it up so that I can keep my workspace very nice and neat. I keep it organized and I can iterate very easily over all of them for any operation I potentially want to do. And I'll use that in a second when I compute AUC. All right, so now what I'm going to do, I want to get the predicted probabilities from all of the models. Okay, so I'm going to use the predict problem method to do this. So over here, I'm going to take every single fitted model I have. Then I'm going to get the modeled probabilities for this. Now there's two levels for my target variable. So I'm going to have two columns being spit out. I don't want the full thing. I only want the model of heart disease. Or I only want the probability of heart disease. I don't want the probability of not heart disease. If I had three levels, there would be three columns in this output that I'm getting here. If I had five columns, if I had five levels, I would have five of these going on. And so since there's only two, one column is equal to one minus the other column. I only need one of them. Let's just pick up that one and not worry about the rest. Makes this a little bit easier. Okay, so now I've got all of this into all the modeled probabilities collected in a list. So this is a list of data frames. Now I'm going to take all those sub data frames and put them together so that each column corresponds to the model that I'm talking about. And then here I'm going to say, hey, name the columns exactly the models I have up here. You notice I have everything exactly as is. That way, if later down the road, if I want to modify something, I can do a control F and I can find every time that bagging classifier happens in my code very quickly, very easily. If I start, being lazy and using shorter names, I can't use control F to find things. This is something that I find very bizarre about almost everyone's coding. Like I copy and paste things 100% so that when I want to find something or maybe do a find and replace, I can just type it in, boom, I get it every single time. I don't have to go searching through it as much. All right, so now this is what the model probabilities data frame looks like. Now, some of these models are going to perform better than others. Yeah, that's just how it's going to work out, and that's okay. So let's go through, and now I'm going to compute the AUC of each of these. Oh, something I need to say about this is that this is over the entire data set. In the original data frame, I stored my train, validation, and test column. Here, I can't see what that is. I'll have to invoke the partition column from the data frame to be able to figure out where each of these lies in terms of the partition. So let's compute the AUC of each model on each partition set. Okay, so most of the time, people are going to focus on the test set statistic. So that's definitely important. That's going to be our honest estimate of how the model will perform. But we want to use all three of my partitions to help me gain insight into what's going on. First and foremost, if I have an overfit model, there's going to be more than likely a big difference between train and test. The training statistic is going to look a lot better than the test statistic if I'm overfitted, more than likely. Also, it can work out that let's say that I have data from the past, from 3 years back, all the way 10 years back. I have data 3 years to today is my test set. So my test set is a different time frame than my training data. Okay, well, things are going to change over time. And if I have two different ways of setting up my train and my test, if I'm using like a different subsets of my data, I know what those subsets are, a difference in training and test or training and validation can help me identify changes in the population so that I can know, hey, whoa, something has happened, something has changed. I need to check this out before I put this into production. Also, you can detect the presence of outliers. This happened to me one time when I was working on a project that I did not take care of all the outliers in the data. And when I built my model, my statistics, my root mean squared error was much better on my test set than my training set. Why was that? Well, I had a very, very, very severe, this is a small data set, a very severe outlier in my training data that I had not addressed. It let me know I had a problem. I went through, corrected my outliers, ran the model, boom, things are looking good. Now, after I go through this, I'm going to select my final model, my final models. I'm going to have a short list, and then they're going to go through parameter tuning. Parameter tuning can take a while. I don't want to use every model structure possible for this. It's not going to be worth the effort. All right, so let's go ahead and compute the ROC AUC score. And I'm going to do this for each model, each partition. And let's go ahead and sort this by the test statistic. So bigger is better when we talk about AUC, area under the curve. And so for this round, we can see that Bernoulli and Gaussian naive Bayes are coming out on top. And they're very tight with extra tree classifier, then logistic regression, linear discriminant analysis, and random forest. Now, I ran this multiple times, by the way, and it worked out that extra tree classifier is consistently coming up at the bottom of this list, which means it's better. And random forest is also coming out lower. And so linear discriminant analysis and the naive Bayes honestly are kind of bouncing around this as I go through and try this over and over and over. I personally would be leaning towards extra tree classifiers off of the data that I've seen because I've done this multiple times. And you'll notice that the AUC really isn't much of a difference off of these. I would probably consider all of these for further exploration for my parameter tuning. Let's go ahead and visualize it. Now, what I'm going to do here is I'm going to sort the bars by the average AUC that I have. Why do I do that? By doing this, overall, the bar should go from lowest to highest. If I see something other than lowest to highest, that's an indication that something is kind of spiking up elsewhere, or it's spiking down elsewhere. And that can be an indication to help me spot, like, if there's something going on with overfitting. And so as I scroll through, anytime I see a bar out of order, that's an indication that something's going on with the other two partitions. So we see Bernoulli, naive Bayes, is pretty far back from here. So that's kind of a weird position to be in, considering it was so low in the overall. While extra tree classifier, random forest classifier, and histogram gradient boosting classifier are all coming out pretty solid. And as I look through here, they look good on the height. So I'm considering all three as I look at this. Now the test statistic is our honest estimate of what's actually going to happen. But by looking at all three of them, I have more confidence on how this will actually perform. Yeah, it's kind of weird that naive Bayes Bernoulli is so low, considering it's, the AUC is, such a weak value compared to it's the best one overall. So something's kind of sticking up at me that, maybe I want to shy away from naive Bayes. And so here's the order on the models going by the average of them. And so I can compare and contrast. If the order doesn't match with the test set, I might want to back off of it. All right, well, that's all I've got for you. Life is short. Do math.